Hi, everybody. We're doing section 2.2, permutations. And permutations are used when we're ordering things. I don't mean, well, I didn't mean ordering food from a restaurant, but I guess, there's probably some math in there also, some permutation math sometimes. But what I mean is, if we want things in a certain order, for example, if I have the set ABC, so how many orders could I do that? I could do ABC, BCA, CAB. Like, how many are there? And we're going to see that it's 3 times 2 times 1, which of course that's 6. And why is that? Well, again, we can see from this tree diagram, when you start, you have 3 choices, either A, B, or C. That's 3 choices. Well, if you choose A, you have 2 choices left, B or C. If you choose B, you have 2 choices left, A or C. And if you choose C first, you have 2 choices left, A or B. Now, once you choose A and you choose B, there's really only one choice left for the third selection, and that's C. In other words, once you do the first 2, there's only one left. Anyway, you have 3 choices here, times each of these has 2 options, and then each of those has just 1 option. By the way, that's always the way it's going to be. Even if we're talking about 97 things, when you got to the 97th, there'd only be 1 option left. But that's the way it is. That's 3 times 2 times 1, which you fancy people know is called 3 factorial. We're going to see that officially in a minute or two. A student is taking 5 courses in the fall semester. How many different ways can the 5 courses be listed? I mean, how many different orders? And the answer is 5 times 4 times 3 times 2 times 1, which is for the same reason as what we just had before. You can make another tree diagram if you want, but that's your business. But like I say, the first class, there are 5 possibilities for the first class. Once you choose the first class, there's only 4 left. Once you choose the second, there's only 3 left. Once you choose the third, there's only 2 left. And so, and notice once you choose 4, there's only 1 left. So the last thing is always a 1. Anyway, there you go. Baseball team. And this is the what we call factorial. And we use a symbol, we use an exclamation point. So 0 factorial, that's kind of by definition. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and then that's 3 times 2 times 1, that's 4 times 3 times 2 times 1, and so on and so forth. Notice this grows very quickly. They say that's why the exclamation point is used. Like, whoa, this thing gets really big really fast. And 8 factorial is already like 40,000 or something, something. So anyway, notice that 4 factorial is 4 times 3 factorial, 5 factorial is 5 times 4 factorial, and so on and so forth. And 11 factorial is, wow, that's a 399,168. That's a big number. So there you go. But what's interesting is that when I divide factorials, let's say 25 factorial divided by 23 factorial. That's like, whoa, that's like that 25 factorial is a humongous number. 23 factorial is humongous numbers. But if I multiply them, really what's going to happen is that everything's going to cancel out. The last 23 numbers on top are going to cancel out with the entire 23 numbers on the bottom. So I'm just going to be left with 25 times 24, which is 600. So a lot of times when you divide factorials, it winds up being, reduces a lot. It becomes easier. So we have a club with 25 members, and they're going to have an election for president, secretary, and treasurer in that order. Assume that a person can hold only one position. How many ways are there of choosing these 3 officers? By the rule of products, we have there 25, because 25 people could be president, but once the president is elected, there's only 24 left who could be secretary. And then once that's done, there's only 23 left who could be treasurer. So it's 25 times 24 times 23, whatever that number is. And we call that a permutation. That's this word right here. When an ordered arrangement, let me highlight that. Permutation. And ordered. The word ordered is very important. And the reason I say that, I'll explain why in a second. of k elements selected from the set of n elements where no two elements of the arrangement are the same is called a permutation of n objects taken k at a time. In our example here, there are 25 taken 3 at a time, 25 members, 3 officers, and the total such number is called P of n comma k, means the number of permutations for n objects taken k at a time. The reason I say order is important because if I would say we have 25 members in a club, and we want to choose 3 officers, but all 3, but not a president, secretary, charge, just 3 officers. So it'll be a committee. It'll be a council of officers. Well, that's a whole different problem. It will not be the same answer because I'm not saying that actually is going to be 25 to the 3rd power because there are 25 people could be the first officer. And hold on one second, please. I'm sorry. I take it back. That's gonna be less, but I don't want to get into it right now. Well, I will. Well, all right. It's too late. I already said something, so let me just get into it a little bit. That's actually going to be this number here. That's actually going to be 100. Will be the final answer. No, I'm sorry. 25 times 24 times 23 divided by 6, because let's say we choose Bob, Jim, and Sally, so it could be Bob. So in terms of those are the 3 people who get chosen. Now they could be Bob, Jim, Sally, Sally, Jim, Bob, Bob, Sally, Jim, so on and so forth. Well, how many possible ways are there? Well, there's 3 factorial, there's 6 ways. So for any group of 3 people, there are 6 different permutations where there's only one just nondescript, what they call a combination. So basically, you have to take this answer and divide it by 6. But we're going to get to that in a upcoming section. We're going to talk about that specifically. But for now, here's the formula. Formula is, drumroll please, that P of n comma k, which is n times n minus 1 times n minus 2 dot times n minus k plus 1. That's going to be the product as j goes from 0 to k minus 1 of n minus j. And that's also going to be expressed as n factorial divided by n minus k factorial. There's these numbers here. If I take n factorial and then not cancel out the last, the n minus k, the last those last k numbers, then I'm going to wind up with this guy right here, similar to what we saw with actual numbers previously. So let's see. Let's look at the proof here. Yeah, so the proof of this is pretty straightforward, and it's like this. So first of all, let's just start when k is actually equal to n. Well, that's P of nn. That means how many groups, how many permutations of n objects can I take n at a time? Well, that's just the same thing as how many ways can I permute n objects. That's just n factorial, which can be written as n factorial over n minus n factorial. So that's cool and awesome. Now, let's say k is less than n. It's between 0 and n. So we have k positions to fill using the n elements. And position 1 can be filled with any of n minus 0, which is n elements. Position 2 can be filled with any of the remaining n minus 1 elements. Position 3, any of the remaining n minus 2, so on and so forth. And finally, position k can be filled with any of the n minus parenthesis k minus 1, which is the same thing as n minus k plus 1 when I get rid of the parentheses elements. So by the rule of products, we have P of nk is n minus 1, n minus 2, which is exactly what the theorem says it is, and the rest is history. Now let's look at an example or two. Okay, so let's do another example of choosing officers. The club has eight members eligible to serve as president, vice president, and treasurer. says 3 officers. How many ways are there of choosing these 3 officers? Well, using the rule of products, there are 8 possible for the president, 7, then there's going to be 7 left who will be vice president, and 6 left who will be treasurer. And that's 8 times 7 times 6, which is 336 ways. And we could have, that's just with logic. Now, the second solution, we could just plug into the formula. E of A3 is 8 factorial over 8 minus 3 factorial. And so that's 8, 7. So let me type it out so you can see it more better. So if you look on the side, 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. They're all multiplied. 8 minus 3, of course, is 5 and factorial. So 5 factorial is 5, 4, 3, 2, 1. Well, if you notice, you have the 5, 4, 3, 2, 1 on the bottom, and you have 5, 4, 3, 2, 1 up here on top. Well, that's all going to cancel, and I'm left with just the 8, 7, 6. And that's where that all comes from. So, that is the story with that problem. I'm going to save this. This is going to be loud. All right. Yes. Yes, I do. All right. Yeah. Okay. Anyway. It's been loads of fun. These are all kind of the same thing. It's been loads of fun, and we'll see you guys next time. That was section 2.2. Bye, everybody. Have fun. See you later.